that ding was the final student. Everybody is here. Awesome. That's working, that's working. Good, good, good. So, good morning, everybody. It is still morning, right? Okay, we're cutting it kind of close with that little shift after. We gotta wait 10 whole extra minutes until lunch. It's gonna kill me. But we've got some very important mathematics to address beforehand. Those wonderful slice and dice conic sections. We talked about parabolas yesterday. And remember, we addressed parabolas with quadratic equations in the first place, those wonderful curves and their nice fancy features. And we found a new feature, the focus, that literally in a physical application of parabolas, you could create a mirror that focuses the sun's rays to heat something to the point of combustion, if you want to go that far. If you didn't want to go that far, you could just heat it up a lot, but not burning, and call it a solar oven. You could make a satellite dish that instead of the sun's rays, you focus radio waves. All kinds of other things. A mirror, right? Just to view and see things. Telescopes make great use of parabolic mirrors, so they can see stuff way far away. Instead of just focusing the sun's light, we're trying to focus that star way out there that has barely a little bit of light, barely getting here to Earth. So we really got to focus it so we can actually see the thing. Okay, that's all of that good, awesome stuff comes from parabolas. So let us review then our worksheet from yesterday. Here are the answers, or at least one version thereof. I don't know why the book insisted on using mixed numbers in there. I didn't think of it until I was like halfway through, and I'm like, why are they doing this? So I apologize if you have these so-called improper fractions. Instead of 3 1/4, you have 3 times 4 is 12, 13 fourths here. I would probably prefer that. Or you could go decimal form, 3.25. I think most of the fractions, at least on the front page, are halves or fourths or something. So decimals, when it comes to fourths, A-okay. I love me some 0.25s, all right? When you get into like 3/7, don't go for a decimal, okay? But here is fine. All right, so there is the graphs and all of the data from each one. Not too terrible. Similar to how we've graphed these by hand in the past, I would approach it as find your vertex first. And especially on the front page, notice A is an invisible 1, so it's not stretched or shrunk in any direction. So know always the shortcut for the standard basic parabola goes over 1, up 1, over 1, up 3. Right? Because in total, it would be over 2, up 2 squared is, oh, sorry, not that far, up from here there. 4, right? So that's how I did these. I just plotted out those 3 points, mirrored these 2 on the other side, and give it a nice smooth curve. So there you go, reminder on how to sketch a nice looking parabola. But the important thing is the vertex. If you don't need these points to be super accurate, just get the vertex for me and the direction of opening. You're set on your sketch as far as I am concerned. We have computers and graphing calculators if we need to have a better picture. Okay, so there's those guys. And then the last ones, including this sideways guy at the end. Nothing wrong with that, except that I said y equals. Whoops, I got so used to writing y equals. That should be x equals in terms of y, because a function of y in terms of x would not actually be a function. It fails the vertical line test. But x as a function of y, well, now we got to turn the whole thing sideways. And yes, that totally works. You can do that. You can say x is a function of y. It passes the horizontal line test. That's a little trick with the definitions there. All right, any questions on the front page? All right, for those of you that went on to level 2, here then is the back page. We've got the equations in standard form, and again, they keep saying standard. We know it as vertex form. I really wish they came up with better names for these things. But this is the general form. General and standard aren't very descriptive for me, but there you have it. Polynomial form versus vertex form. And there's these graphs. These ones do have a of not 1, so you can't use that 1, 1, 1, 3 trick. You will have to actually count. How does this get stretched? Makes it a little bit trickier, but again, if you're struggling with these things, put it into a graphing application first. These are x equals, so your TI-84s would not be able to handle that directly, not the way we know. You could go parametric, but we won't go there. So Desmos for the win. You need to get a picture there. And the next four, there's through number 10. Question number 10 actually is very similar to our how to build a death ray example question we started with. So there you have it. All right. Questions on the back page? All right, then today we move on to that most symmetric of conic sections, the circle. And my notes for circles is really short because there's not as many details. There's not as many fine-tuning bits and features to tinker with like there is with parabolas, and we'll see later the ellipses. They're very basic kind of shapes. Except I'm starting with a triangle. And see why. Because a triangle is really easy to plot on the Cartesian plane. We have our y and x axis. Here's the origin at 0, 0. And I plot a point out at 3 over 4 up. And we know from geometry that, let me go purple. No, we'll stick with blue. The triangle is blue, right in blue. That if I wanted to know, say, what is this distance of the hypotenuse, you would tell me, I use what theorem would help us out here? Tell me in chat. Pythagorean theorem, there you go. Yeah, Pythagorean theorem says that that third side, the hypotenuse squared, is equal to the sum of the squares of the other two legs. So this would be 3 squared plus 4 squared. Of course, if you recognize your special triangles, you would know this is a 3, 4, 5 triangle, so we don't even have to do the rest of the computation. No, we should get 5 is equal to, why is it not writing it? 3 squared plus 4 squared, right? Now, what if instead of that point, this beautiful 3, 4, 5 triangle that just works perfectly, what if instead I had some arbitrary point x comma y out here, and I wanted to know what is its distance r from the origin? I would set up the same thing, wouldn't I? I would say, well, r squared is going to be equal to x squared plus y squared, right? Because you could just draw in at any point here and create yourself a right triangle from any point on the Cartesian plane. Agreed? And if we collect all of the points, all of these that I have dotted along here, that have the same r distance from the origin, that gives us our circle centered on the origin. That is the equation of a circle. Well, usually we write it the other direction. X squared plus y squared equals r squared. Right? So this is kind of neat. Compared to the parabola, notice usually we had y equals x squared. Here we have x squared plus y squared. So both variables are getting squared. And we'll usually group both of them on the same side of the equation, and we'll leave our radius out there by itself. That'll be some constant. This will just say 25, for example. Okay. And the equation actually comes from Pythagorean theorem. We built a circle out of triangles, funny enough, right? Okay, but we can do one better. What if your circle is not centered at the origin? What if we shifted it so that the center is now some hk on the Cartesian plane? Well, we still have a radius. Hey, you know what? It's been a while since I drew this. Oh no, it moved. Don't do that. Trying to get a nice... Oh, there we go. Recent update since I had these notes last year. Can now create perfect circles. Look at that. Beautiful. I don't think it's actually quite on the center there, so I like that. There we go. All right. So what if it is shifted? H, comma, k. Well, remember your parabolas. If I wanted to notice my vertex of the parabola, I would have x minus h squared plus k, right? And so because the x is getting squared, I put in opposite of h inside parentheses to also get squared along with it. Well, in the circle, x and y have the same thing happening to them. That's what keeps the circle so symmetric. X and y are always treated exactly the same. So they need to be given this treatment. So instead of x squared, we have x minus h squared. And instead of y squared, we have y minus k squared. And still all equal to the radius squared. That part didn't change. So all we've done is added this shift of h and k into our circle, but it still overall squares both variables, adds them together, and gets a constant result, because that's that constant distance from the center. Isn't that neat? I love the circle equation. It's really rather elegant to work with. Any questions so far? No? All right, well, let's take a peek at your worksheet for today to see how they're going to test you on this stuff. Somewhere down here, circles, there it is. We've got writing an equation of a circle that satisfies the conditions. Right, so sometimes they'll just give you the information. Hey, here's the center. That's my h comma k. Here's the radius. That's my r. Right, putting that together, very straightforward. Plug them into the standard form, general form, what? Okay, of the equation we just looked at. But other times they'll try to get tricksy on you. Right? They'll ask you things like this. Oh, the diameter has endpoints here and here. How about now? Well, what do you know about where the center is of a circle compared to its diameter? Think about it. Drawing a picture. Here's a circle. Here's a diameter. Where's the center compared to that diameter? How would you describe that? Looking for a key word. Say again? Midpoint. There you go. That's what I was looking for, right? We talked about that on Friday. Hey, that stuff is actually useful. It's a midpoint, although now it's kind of looking like a great ball, but that's just me. Right? The midpoint. Okay, so if you use a midpoint, that'll get you to the location of the center, and, well, then we need the radius. Okay, well, if I have this point, and that point, and that point, now I have the location of these 3 points. I need to get the radius. I need to find a distance. Oh, look at that. We've got a formula for that too. The distance formula, or good old Pythagorean theorem. Again, to find how far these endpoints are from your new center. Right? Not bad. Same with, right, this guy gives you the center, tells you how far away where it is, so you can find how far it is. This guy gives you the center. Tangent to the x-axis. Remember, that means it touches. So that means somewhere on here we have, draw a quick picture, center at -6, +5. Negative, positive. So the center is over here somewhere, and our circle is such that we, boop, touch the x-axis right there. Okay? So you can figure out those 2 points. And if you've got the center and a point on the circle, you can get the rest of it just like you do in the one prior to that, number 6. All right. And then the second half has you go the other direction. Here is the equation. Find center and radius, and then graph the circle. Your graphing utilities might be a little bit difficult because TI-84s in standard form do not graph circles well, not in the y = mode. So we're going to have to rely on our by hand tricks here. So all we need to do is check what is getting squared. X with the +3, remember it's always minus. So we want to subtract, -3. 1, 2, 3, right? And y has nothing on it, so our center is actually right there. And what is getting squared over here? How do you get 16? You have to square a 4, right? So I would go 4 in every direction. Take that radius and go 4, 1, 2, 3, 4 up. 1, 2, 3, 4 down. 1, 2, 3, 4 to the right. 1, 2, 3, 4 to the left. Draw that in, and now start drawing at one point, around, and good enough. Okay? If you need help drawing a circle, if your circles always come out looking kind of like a rounded diamond, more like that, remember tangent lines. You should have a tangent line here, right? Try to get as close to that as possible. So when you're on the top and the bottom, you should be moving your pen perfectly horizontally, just for a little bit. So maybe drawing a little line like that to get yourself started. And then you can just connect them like so. There's my tips for drawing a circle. Right? It doesn't have to be perfect. Right? That's why you put these big dots, so we know where it's supposed to go. And fill in the rest with our imagination. All right, that should do. Watch out on some of these. Hey, what's this doing here? that guy's not part of the squared. You need squares to make a circle. So you're going to have to complete the square here before you can make that work, okay? And make sure you balance it, so whatever you have to add here, go ahead and add that to the other side of the equation to get your actual radius. It's not the square root of 12. Hint, hint. All right, I think I have more than anticipated the major downfalls. Anybody else come up with questions, problems they see on the page? No, nothing stands out. Sounds reasonable enough so far. Then I will leave you with the rest of the period to work, which we go till 12:30 today. I thought it was 10 minutes later. I guess it's a 15-minute shift, isn't it? Yeah. Till 12:30. My goodness, you've got 25 minutes to work. You could almost finish this thing. Certainly level 1, maybe even a level 2 finished worksheet already. Have at it. Let me know if you run into trouble and do have a question as you go.